Good morning, everyone. I'm CEO from Seafloor Mineral Resources. Today, I'd like to share some new insights into the gold enrichment process in a deep-sea hydrothermal chimney. I think most of you are quite familiar with this video. It's a deep-sea hydrothermal vents, and they keep discharging the black fluid. The fluid are black because they contain fine-grained sulfides. So does the chimney. They also contain a lot of the sulfide and also sometimes the precious metals like gold and silver. They are also very important habitats of living organisms. The deep-sea hydrothermal system has been suggested to be the modern analog of the ancient volcanogenic massive sulfide ore deposit. So by studying the modern hydrothermal vent, it can provide us a good understanding of the ore forming process of the ancient ore deposits. To begin with, I'd like to share a little bit background. How does it form? The chimneys are formed due to the quick mixing between the venting fluid and the cold seawater. And the venting fluid are generated during the circulation of seawater within the oceanic crust. And the whole process was motivated by the heat from the magmatic activities at the depth. The metals have been can be sourced from the leaching of the oceanic crust and also sometimes contributed by the magmatic fluid during the degassing of the underlying magma chamber. The chimneys usually feature zonation textures with the temperature gradient from high to low from interior to exterior. So usually the chimney features with a chalcopyrite interior, which then transits into the sphalerite dominated area and then the sulfate and oxides exterior. This is the chimney sample I have been studied in the last couple of years. It was collected from the East Manus Basin by the Surrey research team 30 years ago. The Manus Basin is close to the Papua New Guinea, and it's a back arc basin, which was formed due to the subduction of the Saloma microplate into the Bismarck microplate, resulting in a series of extension structures here. So in Eastern Manus Basin, number of the venting fields that are developed as indicated by the yellow dots here. Those venting fields, they were hosted by the basalt, dacite, and andesite. The sulfide chimneys contain elevated gold in this area. The average concentration of gold is 11 ppm, with the highest can be up to 56 ppm. However, in previous studies, it's generally very difficult to quickly locate the native gold because they're very tiny in the sulfide. And you may have to spend a long time to look at them with the optical microscope. So in this study, we applied a combination of synchrotron XRF elemental mapping and also EBSD microstructure and crystal mapping to calculate the gold and try to figure out their precipitation mechanism. So this chimney sample is not a perfect chimney, but it's very informative. There's a lot of holes there, and there's a pathways of the fluid passing by, and this void is always rimmed by yellowish chalcopyrite here, and then transits into the greenish sphalerite dominant zone, and then covered by a brownish and orangish the sulfate and the iron oxide exterior. So we did today we present a study from this section. So this is the synchrotron XF for scalar map. Yellow color indicate chalcopyrite, and red is pyrite, and blue indicates sphalerite. The black is a void. So gold have two occurrences from the synchrotron map. First type gold is closely associated with a tannatite and tetrahedrite here. And the second is very interesting. Gold occurs linear and concentrate on the boundaries of chalcopyrite. This is a new observation which has not been reported before. Okay, so now we know where the gold is. So the next question is to understand why they're there. So before we try to understand this question, we need to figure out or have a good understanding of how this chimney conduit are formed. They look like similar with the previous studied chimneys. So let's see what the EBSD microstructure of this sulfide can tell us. So if you take a look at this region and zoom in, so it looks quite simple from a central image, just dominated by chalcopyrite, yellowish here, and segregated by gap. However, the SEM image show that the gap actually contains a lot of sphalerite here and also some native gold. And also some pyrite grows outward based on the sphalerite layer. Okay, now I'm going to show some interesting about the EBSD, the microstructure feature of this region. So this is the four scatter detector image, was similar to the BSE one. If we overlay it with a backscatter image, so you can see a lot of lines. So the light green lines indicate green boundaries. So is that so you can see these are crystals. So this whole image shows the distribution of the microcrystals of all the sulfides. So here we can see actually the chalcopyrite grows two directions, interior and exterior respectively. If we zoom in the sphalerite layer area, so we can see actually it contains a lot of fine-grained particles. What does it mean? The clusters of the fine-grained particle usually indicate the supersaturated conditions in the venting fluid. So this suggests that these layers is likely to be an initial layer result from the quick mixing between the hot venting fluid and the cold seawater. And then during the further mixing, the pyrite and the chalcopyrite continue overgrowth from this layer. Okay, now let's take a look at gold. As I mentioned before, the first type of gold is associated with tennantite and tetrahedral mineral. The currency of this mineral indicates high sulfur activities in the venting fluid. And the gold has also been suggested to be transported as gold bisulfides, this complex in the venting fluid. Therefore, gold is likely to precipitate due to the mixing between the venting fluid and the seawater, which will reduce the sulfur activity and drive gold precipitation. Then we took a look at the second type. Is gold occurs on the boundary of chalcopyrite wall. The SEM image shows us another two different gold currencies. So gold occurs together with arsenic pyrite. So you can see the gold particles on the arsenic-rich pyrite. This observation is very common to be observed in the hydrothermal gold deposit. We all know that the arsenic during the arsenic pyrite precipitation, the arsenic can help to accumulate the gold into the pyrite. So here we interpret that gold is precipitated together with its arsenic pyrite during the fluid mixing. If you look at the second one, very interesting. So the gold only precipitates on the boundaries between the early sphalerite and the chalcopyrite layer here. We did EBSD analysis on this as well. We look at the small area. So it's very interesting. We found out that both chalcopyrite and sphalerite share one crystal. For example, here this is one crystal, but the top is copper-rich, indicates chalcopyrite, and the bottom is zinc-rich, indicates sphalerite. And the gold occurs as nanoparticles on the boundaries between them. We interpreted that the gold will precipitate due to the overgrowth of chalcopyrite on the sphalerite here. We also find similar observation, but maybe not exactly, in the fossil chimneys from Silurian VMS deposit. So in this chimney, very close to the center, we found that the authors here reported that their thin sphalerite layer segregated the different generation of chalcopyrite, and the sphalerite is gold-rich as well. So here we propose that actually the thin sphalerite layer represent the early stage of the fluid mixing. It's very common in in fossil and modern chimneys, and they are gold rich. So if one to target for native gold in such samples, then this could be the potential area you should target. Okay, so take-home message. Our study shows that the chimney conduits they actually form at different stages, and each stage may correspond to a type of mechanism for the gold precipitation. The textures are primary, which has not suffered any metamorphism or hydrothermal alteration. They can be the potential indicator to identify the fossil chimneys in the ancient VMS deposit. And we also suggest that the analytical package we use can be potential useful tools to calculate the ore forming process in other similar ore deposits. In the end, I'd like to express my acknowledgement to my collaborators from Curtin University and Verrall and the Australian synchrotron. Also, I'd like to share this and Verrall Mineral Resources. We are multiple disciplinary and diversity team focused on the future, driving change and delivering impact in mineral exploration by varying diversity and inclusion. Thank you for listening.